Okay. Yeah. Sorry, I forgot forgot my mic, so I'll just talk. I don't want to shout. It's hard shouting. So, um, we're in week 8. It's so crazy to me. And then, but anyway, we'll start our week of lectures, I guess, on clustering. The topic will be unsupervised learning and clustering, and so that's what we'll look at today. So all the methods we've learned so far have been supervised learning methods. Okay, and so the way supervised learning works is that we take input values and we've got output values, and we try to get the output values to match as closely as we can to get our targets. So things like classification, you had the correct classification, the target. For the iris data, you knew that this was setosa and this was versicolor and this was virginica, and so you wanted to get your predictions to match that as closely as possible. With unsupervised learnings, we don't have any kind of target values. Okay, we just have our data, and we're looking for structure in our data. Okay, and so we'll start off with kind of some clustering methods, and clustering is just the idea of trying to group similar observations together. Okay. And then later on we'll look at dimension reduction, which includes PCA. Actually, that's probably the only dimension reduction thing we'll look at. But that'll probably be like next week, okay? So, as far as clustering goes, we've got, your input matrix X, and the idea is to kind of form groupings of these things so that the objects within a group are similar to each other, defined by some metric of similarity, and then objects in different groups are not similar to each other. Okay, and you got different ways to measure similarity, applications are things like grouping products together if you're a merchant, or documents. Or like physical locations. These are all, I would say, common applications of clustering. Okay, so if you wanted to just kind of create groups of some kind, and so the kind of the initial simple clustering method that we often look at is called k-means clustering. Okay, and this is kind of your basic clustering algorithm, and the way it defines object similarity would be in terms of Euclidean distance. Okay, so you just measure, where's this point and where's this point, and you measure the distance between those two things, and that's going to measure, how similar things are or how different things are. Okay, and okay. And so the name k-means and k-n-n are kind of similar because they both start off with k, but don't get them mixed up, right? So k-n-n is a classification algorithm. You use that to look at your nearest neighbors to decide what class a certain thing belongs to, and k-means has no class labels to start off with, and you're just using it to group things. Okay, but in k-means, our clusters are defined by centroids, okay? And so the centroid is just the mean of the points assigned to the cluster in it, and we're assuming X is multidimensional, and so it's going to be your multidimensional mean. So if X exists in 2 dimensions, your mean will basically be the coordinate of the in 2 dimensions, the centroid in 2 dimensions. Or if it's in higher dimensions, you'll have if you got 7 dimensions, if your data comes in 7 dimensions, your centroid will be in 7 dimensions as well. Okay, and so basically it's just the sum of the x's divided by how many belong in the cluster. And so z is a variable for whether the point belongs in the cluster or not. Okay, so you're taking the x's, and then if it belongs in the cluster, you add it, and if it doesn't belong in the cluster, it zeroes out, and then you divide by how many points are in the cluster, and that's going to give you your mu vector. It's really simple, and so the algorithm works in an iterative fashion. It starts off by you define how many clusters that you're going to search for, and then there's a few initialization things. I say just randomly assign your points to the clusters at random. Other things will just say start off with arbitrary points for the clusters. It doesn't really matter, okay? Randomly assigning the points. This step doesn't matter, okay? And basically the algorithm comes down to these two steps 2 and 3, okay? Once all the values have been assigned to a cluster, you calculate the centroid, and then after you calculate the centroid, you reassign values to the cluster, okay? And you associate them by using by assigning them to the cluster with the nearest centroid. Okay, so if you've got if you're searching for k equals 3 clusters, you're going to have 3 centroids, and then you're going to take each point, measure its distance to each of the 3 centroids, and then whichever centroid is closest, you assign that point to that centroid, okay, or that cluster. And then after all the points have been reassigned, you recalculate the centroids, and you do step 2 again, calculate the centroids once all values have been assigned, calculate the centroids, and then you reassign the values to the clusters, and then you go back and forth, okay? And that's it, okay? Maybe the hardest part is determining how many clusters to search for, and there's not necessarily a straightforward answer, and people will disagree on something like this. So for example, the census is coming up, and one of the things you can check is going to be your race or ethnicity, and the idea is can we group people into different kind of categorical groups or something based on race and ethnicity, and there's always a question of how many races are there, right? How many ethnicities are there? And this is a question that doesn't have a simple and straightforward answer, okay? And if you have complex data, people will disagree and will say, oh, there's only this many clusters or whatever, and then someone will say, no, you can take a cluster and you can further split that into another cluster, right? So oftentimes, like for race, there might be like an Asian category, but then that can also be further subdivided into however many ethnicities somebody deems fit. East Asian, South Asian, Southeast Asian, and Central Asian, and then further split those into nationalities and things. So picking how many clusters you will search for, this is. I don't know if there's a straightforward answer to any of this, okay? Because there's no defined labels, right? This is an unsupervised learning task, and so you're just kind of searching for structure, and you might find different structures, okay? All right, so here is a toy example. Oh, I don't know what happened with the rendering here. This is, in the toy example, there's 4 points up here, and there's 4 points down here, okay? And so I'm going to just start off and say we're going to search for 2 clusters. And so the points, I don't know what happened. Okay, the points are 0, 0, which is down here, 0, 1, 1, 0, 1, 1. and then I've got 3, 3, 3, 4, no, 3, 4, 4, 3, and 4, 4 up here, okay? And I'm going to just randomly assign them to clusters, okay? So I'm going to just say, we're going to just choose 1 or 2 at random, okay, using sample 1 or 2 with a replacement, and I need 1 for each row. Okay, so I'm going to get assignments is going to be a vector of 8, and it's just going to be 1 or 2. And so after, okay, let me just show you what it should look like over here. Okay, so this is what it's supposed to look like. I got four dots up there, 4 dots down in this corner. Okay, and then I randomly assign them. Okay, and then so with the random assignments, I got 3 dots up here, and or 3 red and 2 red, a total of 5 red, and then 3 assigned to black. Okay, so these are kind of the random assignments at this point. Okay, and you know, before even doing any of this stuff, like if I told you to cluster these into 2 clusters, it's obvious that we would pick this and pick this, right? This is just a toy data set to just kind of illustrate what's happening. And then what we do is we calculate the centroids of each of the quote clusters. Okay, so if we look at the 3 dots assigned to black, we've got 0 in the x1 direction. I've got 0, 0, and 3. Okay, and so so the mean of those points. So if I do 0 plus 0 plus 3, I'm going to get 1. Okay, so if I look at this row is assigned to cluster 1, and so is this row here. Okay, so looking at x1, I've got 0, 0, and 3, which gives us a mean of 1. And then in the x2 direction, I've got 0, 1, and 3. Okay, so 0 plus 1 plus 3 is 4, divided by 3 gives me 1.33. I do the same thing with those that are assigned to cluster 2. Okay, I've got 1, 1, and then down here I've got 3, 4, 4. So 1, 1, 3, 4, 4 adds up to what is that? 8, 11, 12, 13. 13 over 5 is 2.6. Okay, and then looking at x2, I've got 4, 3, 4, and 0, 1, and that gives me a mean of 2.4. Okay, and we could also, probably easier just to use dplyr or something like that, or use an apply function. Okay, and so yeah, I create a data frame, because dplyr runs off of data frames. So I make a data frame between our X matrix and the assignments, and then I group by the assignments, and I ask, you know, what's the mean of x1 and what's the mean of x2, and it comes back and it gives me 1, 1.33, 2.6, and 2.4. Okay, so so no problem, and okay, and let's see. So I reassign the points here. Okay, yeah, something's going on again. All right. What? Okay, randomly assign these. Still have no internet, huh? Okay. Okay, and so so this represents the centroid of the 3 black dots, and then this represents the centroid of the 5 red dots. Okay, so we've got this and this, and so now we will go through and we will assign every point to the centroid that is closer, okay? And so it's quite clear that these points, these 4 points are closer to this one than they are to this centroid, and these 4 points are closer to this centroid than this one. But just to kind of illustrate how it works is, you know, we look at this point, we measure its Euclidean distance from here to this centroid, and you know, from the dot to this centroid. And so after we measure that, we're going to say, okay, this centroid is closer, so it's going to be assigned to the black cluster, okay? And so that gets assigned to black, and then you know, we measure these two distances, and again, the distance to the black centroid is closer, so so these points all get assigned to black, and then when we look at these points over here, we measure its distance to the two different centroids, okay? And again, these centroids were calculated based off of the initial random group assignments, okay? So that's where these centroids are based on. And then we do the same here, and we can see, okay, the distance to the red centroid is closer than to the black centroid, and so this dot will get assigned to red, okay? And then same thing with here. You know, we look at the two distances, it's closer to red, so it gets assigned to red, red, and red, okay? And so, so after the reassignment, these, you know, we've got 4 red over here and 4 black over here. And then so after we reassign, we redo the process and we recalculate the centroids, okay? So we've got 4 dots or 4 points assigned to the black cluster, and we're going to find the centroid of the black cluster. And we've got 4 dots assigned to the red cluster, and we're going to find the centroid of the red cluster. And so again, here I've just run dplyr, and so the centroid of, I guess, centroid 1, or the cluster 1 is 0.5, and the centroid of cluster 2 is 3.5, 3.5. And so we do that. And so here's the centroid, and here's the centroid there. And then if we tried to reassign clusters, you know, none of the group assignments would change, okay? All 4 of these would still be assigned here. All 4 of these points would be assigned here. And when none of the group assignments change, we say the algorithm has converged, okay? So there's no more changes of group assignments. That has converged, and this is the resulting clusters that it has found when k is equal to 2. All right? Yes, question?
Are there ever instances or applications where one or, I guess, a few points would be like weighted more than others?
Where some points are weighted more than others? Not in this regular straight k-means thing, okay? We'll look at the EM algorithm, and in the EM algorithm, you have maybe like soft or probabilistic assignments, and you will say like this point is probably in this cluster, and it could be in the other cluster, but it's less likely. And so when you go and calculate like what's the center of this cluster, you weight the points by their kind of probabilistic assignments. But in k-means, it's just whichever one's closer, that's the one you belong to. Okay, but yeah, it's a good idea, and it gets employed in a different algorithm. Yeah, so k-means is just strict. Which one? You've got a distance metric, okay, and right now we're using Euclidean distance. The distance metric could be something different though, and probably in our next lecture we can take a look at some different distance metrics. But today we'll just look at Euclidean distance. And so this is what happens after doing Euclidean distance, okay? So here's just another mixture. I created 3 clusters. And maybe I should just show you what the data look like without any...
What do you mean by created them? Shouldn't you assign them randomly?
Yeah, okay. So in the data generation, I generated like one cluster and another cluster and another cluster, okay? So in the data generation. But yeah, we just, for k-means clustering, I'm going to just say, I'm going to look for 3 clusters, okay? And so it just randomly assigns the points here. So this is just kind of this big mix of points, but we're going to ask it to try to identify 3 clusters. And we're not quite sure how it's going to do this, okay? And so these are just the random points that it's got. We've got some black points, green points, and red points, okay? And so the first thing it does is it takes all of these things, and just based on the random assignments, we say, all right, what is the mean of the black dots? What's the mean of the red dots? What's the mean of the green dots? Okay, and so we do that, and it calculates the means. Okay, and you'll have a homework assignment where you have to do this. So I'm kind of hiding the code a little bit. Okay, and so when you calculate the means of all of those dots, this is what you get, okay? So just by random chance, the black dots happen to fall a little bit more over here, and so we get the mean right here. The centroid is there. The green and the red are quite similar, but not exactly the same, and so we get a centroid right here, and we get a centroid over here. Okay? And so now we do, so after we've calculated the centroids, we reassign all the points, okay? And so we look at every point and we just say, which centroid is this dot closer to, okay? And so, so basically all of these over here are closest to the black dot, right? And then everything over here is going to be closest to the green dot, and it's really just the points that are kind of in between here. We can probably draw a straight line that creates a boundary between the black centroid and the red centroid, and then you know, down, if I draw a line here, you know, the points on this side will get assigned to black. The points on kind of in this little narrow window here will get assigned to red, and then you can also draw another line like kind of splitting right between the red and the green, and then there will be a couple points here that are closer to red, and then a few points that are closer to green, okay? So basically we're going to get mostly black on this side, mostly green on this side, and then like a thin sliver of red in the middle, okay? So this is what we get, okay, after reassigning all the points. Does that kind of make sense? So this is our, we start off with these random assignments, we calculate centroids, and so these are basically just kind of mostly similar locations, and then we reassign the points accordingly, okay? And you can see indeed pretty much everything over here got assigned to black, everything over here got assigned to green, and then there's just a thin sliver of points that are considered red, okay? So after we've done the reassignments, what we do is we recalculate the centroids, okay? So these are all the points that have been assigned to black, okay? And so we're going to calculate what is the centroid of all of these points, okay? And so that's going to probably be somewhere around here, okay? All of these points have been assigned to green, and we're going to ask what is the centroid of all of these green points, okay? And that's probably going to be somewhere around here, okay? What's the middle of all of these green points? And then there's only a few points assigned to red, but we're going to ask, you know, what is the mean of these red points, and that's probably going to be somewhere around here. So we're going to see, in the next slide, we'll see the centroid move over to here, and then the centroid move over to here, and then the centroid for the red over here, okay? And so this is what we get. So this is where we started off. We reassigned, we recalculate the centroids, and this is what we get, okay? And then we iterate again, all right? And so we say, all right, so these are now the centroid locations, and we're going to go through all of the data and reassign each point to whichever centroid is closest, okay? And so again, everything over here will get assigned to black, everything over here will get assigned to green, but now we've got some question about, you know, which points are black and which points are red, and we'll probably draw like a line somewhere, you know, halfway between black and red, okay? Okay, we're going to draw a line probably halfway here, and so all of these points that are assigned to the black centroid are actually closer now to the recalculated red centroid. And so these points over here will get reassigned to red. Same thing over here. These points, which were originally assigned to the green centroid, when after recalculating the centroids, are now closer to red, and so they're going to get reassigned to red, and we'll see that. Okay, so after recalculating the centroids, this is how it looks after reassigning the points. Okay, so here's our new centroids. We reassign points based on our new centroids. Okay, and this is what we have. And so now that we've reassigned some points, we're going to recalculate the centroids again. Okay, so red probably won't shift too much, just a little bit. But as far as the black cluster goes, the centroid is going to probably shift closer to over here. This green dot will, its centroid will probably shift a little bit closer over here. Okay, and so we recalculate the centroid again, and we get this. Then we reassign points. Okay, and we get this, and then we recalculate the centroids after reassigning, and they shift a little bit, and then after shifting a little bit, we reassign points. Okay, and then we see that after reassigning points, nothing has changed, and so we would say it has converged here. Okay, so this is just kind of where we started. Okay, random assignments. We reassign points, or random assignments, we calculate the centroids, reassign points, recalculate the centroids, reassign points, recalculate the centroids, reassign points, recalculate the centroids, and then we reassign points, but nothing has changed, and therefore our algorithm has converged. Okay, and so these are using k equals 3, these are the 3 clusters it has identified. Okay. And again, all we're doing is just reassigning points based on Euclidean distance, and then we're finding the centroids based on the means. Yeah.
How quickly does it converge?
It depends. Yeah. And where it converges is going to be different depending on your starting points and stuff. Okay. So in this case, because I generated the data myself, I can actually look at, this is how the data was generated, and I said, you know, I'm going to make a cluster over here, and a cluster over here, and a cluster over here. And so we could see some of the points didn't get assigned, I got to fix something here, but some of the points didn't get assigned properly, like these 2 points actually belong to the red cluster, and or the, I guess the left cluster, or actually, so this point belongs to the left cluster, and this point up here belongs to the center cluster, but after assignment, well, I guess this one got assigned to the center cluster, and this got assigned to the left cluster. The colors of the clusters are completely arbitrary, okay? Because it's unsupervised, so it doesn't know that this should be cluster 1 or cluster 2 or cluster 3. And so you could run, like if I started off with a different set of random assignments, I could very well, I'm probably going to end up with the same centroids, the same 3 centroids, but this one might be colored black, and this one might be colored green, and this might be colored red, okay? Just because it's a random thing. And that doesn't matter. The important part is you've identified 3 clusters, and you know these points belong to, you know, one of the clusters, and these ones belong to the other cluster and whatnot. Okay. So it ends up pretty similar. This data was generated using just random multivariate Gaussian. Okay. Does k-means clustering just with its function k-means, okay? So I think in your next homework assignment, I know I just gave you a homework assignment, but you'll get another homework assignment on clustering, and you'll write your own version of a k-means function, okay? Which shouldn't be terribly hard, okay? It's coding, okay? But it'll force you to be aware of what's happening. Okay, but anyway, it's really easy to run k-means clustering in R, okay? You just call k-means, you give it your matrix of data, okay? And then you say you're searching for 3 clusters or 3 centroids. And this is the results. Here I've just plotted the data, and these are the 3 clusters that it has identified.
It colors them for you?
Huh?
It colors them for you?
If the colors, what?
It colors them for you?
Well, so here I did plot the data, and I did color based on results $ cluster. So when you do k-means, it's going to return a list of stuff in your results, and so if you use the cluster assignment to color the data, it will color them like this. Okay, so this is just a cluster. This cluster vector is like assigned to 1, 2, or 3 or something like that. Okay, and so so this is if you ask for the printout of what k-means in R produces. It produces this. It's going to tell you where the means of the 3 clusters are. Okay, it gives you the vector of cluster assignments. Okay, and so in the original data, I just the first 100 rows were cluster 1, the next 100 were like cluster 2, and the last 100 were like cluster 3. And so we could see kind of that similar structure here as well. With a few points being assigned to one of the other clusters, and those are probably kind of the edge cases. And then it also returns something that compares the how much variation is explained by the clusters. It's kind of like an ANOVA regarding if we split the data into these clusters, into these groups, how much of the variation is explained by the groups, right? So in ANOVA, you've got kind of the between group variation and the within group variation, and it returns kind of that metric. So this is almost like an R² value based on cluster assignments, right? If you want to find certain things, you can actually, the results themselves are in a list. Okay, so you can use results $cluster, results whatever, and so we can just kind of look at the within sum of squares, right? So if you've got the between sum of squares and the within sum of squares, the within sum of squares is kind of your residual sum of squares, right? If you're thinking ANOVA, where you've got the total sum of squares in the data, and then you split that down into between groups and within groups, this total within sum of squares can be thought of as like your residual sum of squares. And so we can use this measure, this residual sum of squares, as a metric to help us determine maybe the appropriate number of clusters to use. Okay, so so over here, my R² value with 3 clusters is around 86%. Here I tried using only 2 clusters, k equals 2, and I get an R² value of around 70%. And this is kind of what the assignments look like. If you say I only want 2 clusters, it kind of splits it in half, and this is what it gets. If I used k equals 4, I get an R² of around 87%, and we can look at the between and within sum of squares, and this is kind of the results that it gets with 4 clusters, right? The thing is if you use, no matter what you do, like if you've got k as your k increases, if you run it again, you might end up getting different assignments, okay? Because the initial assignments are random, okay? So based on our initial assignments, it converged, and this is what it arrived at, okay? It produced our 4 clusters, and after it produced kind of this, no points were reassigned, and so this is where it converged to, okay? But I ran it again, using the same thing, k-means, with 4 clusters, and it produced this time, okay? So over here, the kind of the leftmost cluster got split into kind of, into 2. When I ran it again, the center cluster kind of got split into 2, okay? And that's with k equals 4. And so depending on the initial random assignments, when you do different runs, you might end up getting different cluster assignments, and this also kind of makes sense. Again, if you asked 2 people to say, pick out, if you say, all right, we've got space for like 10 ethnicities, 10 races or ethnicities or nationalities to include on the census form, and you give it to 2 different people, you're probably going to get 2 different lists of 10, okay? There's not going to necessarily be agreement on which races or ethnicities to represent if you're limiting yourself to a certain number. And this is always going to be the trouble with any kind of trying to put people into categories. There's never going to be an agreement of exactly how many categories there are and which categories need to be represented. And so, the algorithm doesn't have this dilemma. It just goes through and it follows the rules, and it ends up at different kind of converging points at the end. Okay, so how do we even decide what k to use? It's a little bit tricky, and I don't know if I have a great answer. But one suggestion is you could try out different values of k and just kind of see how things go. All right. So here I create an empty double frame, right? So empty data frame with 2 columns, k and within SS, okay? And both of these are going to just start off with kind of these empty things, and all I'm doing is I'm taking the results. I run k-means with k clusters, and I have a loop within a loop, which is always kind of like, you shouldn't do this in R, but I did this first. I think it's easy to understand. So I'm going to run k for k equals 1, 2, 3, up to 10 clusters, and then for each of those, I'm going to run the k-means algorithm 20 times. Okay, so I'm going to run k-means 200 total times, and each time I run it, I'm going to take the data and split it up into k clusters. Okay, so I'm going to split it into 1 cluster 20 times, 2 clusters 20 times, 3 clusters 20 times, 4 clusters 20 times, and we're going to just each time I'm going to append what my k was and what the resulting within sum of squares, kind of my residual sum of squares, was at the end of it. Okay, and so so I run that, and so every time I ran it with 1 cluster, I got the same within sum of squares, which makes sense. Okay, that's going to be equal to the total sum of squares. You've got 1 cluster, you're going to just have the total sum of squares. Every time I ran it with 2 clusters, I got the same exact results with 1,356 for our kind of within sum of squares. If I inspect the tail of the data frame, though, when I ran it with 9 clusters, my within sum of squares differs a little bit. Okay, I got 279, 264, 281, 260, 263, 265 happened twice, so I ended up with the same cluster assignments twice when I ran it with 9, but each time I got something slightly different, also slightly different with running with 10 clusters. And so what I've done is I've produced kind of a box plot, and the bottom axis got cut off here. But basically, with one cluster, this is the within sum of squares. This is actually a box plot. It's just all the values are so close to each other that well, they're all the same value with 1 and 2 that you don't see any variation here. With 9 and 10, you get you might be able to see kind of the top whisker and bottom whisker slightly with a little bit of variation. But what we see is that with one cluster we've got a lot of sum of squares, and then as soon as we introduce a second cluster, we reduce that within sum of squares dramatically. At 3 clusters, we reduce it quite a bit more, and every time I add more clusters to it, it goes down further, but we can see we're getting diminishing returns. And so this kind of L bend in the how complex we should make our model versus the kind of the gains and the benefits that we're getting diminishes. And so looking at something like this, we would probably choose 3 clusters, which aligns with what we know regarding how the data was generated. But people might again decide to use a few more clusters or something like that. Okay, is that all right regarding k-means clustering? It's pretty simple. You just start off with random assignments, calculate the centroids, which are the means, reassign based on which one is the closest mean. But again, you could use different distance metrics and find different measures of center. So if you wanted to use Manhattan distance, okay. So normally, like if you're at 0, 0, and 1, 1, your Euclidean distance will be square root of 2, right? Manhattan distance will be like how many blocks you had to travel, and you had to travel 1 block east and 1 block north, so it has a distance of 2. And if you use that, then you would use the median or the medioid as your center, okay? So instead of using the mean, you'd use the medians and things like that. I guess we can talk briefly about that on Wednesday as well. Okay, we'll end here, and we'll see you guys on Wednesday.